Hello, so this is going to be a GCSE Science, Combined Science Trilogy past paper walkthrough. This is Physics Paper 2, higher tier, and this is the paper that was sat in June 22. So what I'm going to do, go through and model it, how I would have tackled it, and I've put the link to the mark scheme and the paper in the description below. So figure 1 shows a longitudinal wave. Which do the labels A and B on figure 1 represent from the box below? Okay, so you've been told it's a longitudinal wave. You should remember that particles in a longitudinal wave vibrate parallel to the direction of travel. So our wave is going this way, but our particles are vibrating parallel left to right. When I've got an area of particles that are together, we call it an area of compression. But when they are spaced apart, like in A, we actually call it an area of rarefaction. Now this is just one of these words that you just need to know. Okay, it doesn't really come up anywhere else, but rarefaction just means the spreading out of particles. And then B, the difference or distance between two areas of compression would be our wavelength. Okay, and that's it for a longitudinal wave. The wave shown in figure 1 has a frequency of 4 kHz. Calculate the period of the wave, use the equation sheet and give the unit. Okay, so when it's talking about period of a wave, it's talking about the time period of a wave. It tells you on your equation sheet, period is 1 divided by the frequency. So we know it's 1 divided by 4 kHz, but this equation is in hertz. Each kilohertz is 1000 hertz, so 4 times by 1000 is 4000. So 1 over 4000 gives me a time of 0.00025, and because it's time, it's measured in seconds. And that would be my 4 marks there. Sound waves are longitudinal. Figure 2 shows how the speed of sound varies with the temperature of air. So I've got increasing temperature and the increasing speed of the sound in air. Use the physics equation sheet to answer questions 1.3 and 1.4. Write down the equation that links frequency, wavelength and wave speed. You look on your equation sheet and wave speed is frequency times by wavelength. A sound wave with a frequency of 300 Hz travels through the air. The air has a temperature of 28 degrees Celsius. Determine the wavelength of the sound wave. Okay, so if I know wave speed is frequency times by wavelength, I want to find wavelength, then it would just be wave speed divided by frequency equals wavelength. So therefore, I know my frequency, which is 300, but I don't know my wave speed. Well, for wave speed, I would get using my temperature and my graph, which I've been told, figure 2. So I go back to figure 2 and look at 28 degrees, get the scale right, which would be here. So 28 degrees, go up to your line of best fit and across. Okay, and then making sure I'm reading that value really accurately, and it should be 348. So what I would then do is 348, which is my speed, over 300, gives me 1.16 metres, and that would be my final 4 marks there. So that is question 1. Okay, so question 2 then. Figure 3 shows the competitors in a wheelchair race at the London Marathon. The distance of the London Marathon is 42,000 metres. You've got figure 3 here. Use the physics equation sheet to answer these questions, 2.1 and 2.2. Write down the equation that links distance, force and work done. Well, if you look at your equation sheet, work done is simply force times by distance. During the race, competitors work against air resistance. The work done against air resistance by the winner of the race is 3,360,000 joules. Calculate the average air resistance acting on the winner of the race. So first of all, let's figure out what we're actually working out. Well, we've been given joules, which is energy, and in the early bit of the question, always make sure you read all the parts, we've been given distance, 42,000. So we've got energy, and we've got distance, which is 42,000. So therefore, air resistance, what we're calculating, is our force, which hopefully you would have recognised anyway. So if I substitute it into the equation like that, 3,360,000 joules of energy equals our force times by 42,000. Therefore, rearranging it, our force is equal to 3,360,000 divided by 42,000. And if you do that on your calculator correctly, that gives you a final answer of 80 newtons. Then use the physics equation sheet to answer 2.3 and 2.4. Which equation links distance travelled, speed and time? If you look at your equation sheet, it's just the top one. Distance travelled equals speed times time. The distance of the London Marathon, it tells us again, is 42,000 metres. The winning time was 5,600 seconds. Calculate the average speed. So instead of distance is speed times by time, we're just rearranging it to do speed is distance divided by time. Distance is 42,000. The time is 5,600. Put that into your calculator and hopefully it would give you an answer of 7.5 metres per second. There's no unit conversions needed, it's all relatively simple, which is, a good question. Question 2.5 then. Explain why the speed of a competitor changes during a race. 4 marks. So this is quite an open question, okay? So what you just need to think about is the variables that might affect the speed of a competitor during a race. Well, if we think of a race, generally, what happens at the start, everyone starts off really quickly because they've got more energy. So at the start of a race, competitors' speeds increase as they accelerate, as they have a lot of energy. However, what happens as the race progresses? Energy levels drop, and therefore the speed of the competitors would probably decline. As the race proceeds, the energy levels of the competitors drop and speed decreases. Okay, so saying that would probably get you 2 marks for that. Okay, then you need to think about other factors that might affect the speed of a competitor. Well, it's an open track and it's a marathon, so odds are the surface is going to change or the route is going to change. So the speed would be affected by the route. Okay, specific, if it's uphill, speed would decrease. Obviously running uphill, harder than running downhill. Then you could also say other factors like at the end, a competitor might sprint to the end of the finish line. At the end, speed might increase as a sprint to the finish line. And there are various other things that you could say. You could say about a competitor going around a bend, and bends might slow a competitor down. You could also say about, because it's all about a wheelchair, getting a puncture, which that would decrease or make it stop. Or there could be other other resistive forces on competitors, so their speed might go up or down. Okay, so generally these would be, it's a bit of a strange question, this one, because there's so much you can write about, but take it for what it is and answer it as clearly as you can. Okay, that's the end of question 2. Okay, question number 3 then. Figure 4 shows a child playing with a small train. The train is on a bridge. When the child lets go of the train rolls down the bridge. The momentum of the train at the bottom of the bridge is 0.216 kilograms meters per second, and the mass of the train is 180 grams. Calculate the velocity of the train at the bottom of the bridge. Use the physics equation sheet. So we've been given momentum, mass, and we're after velocity. Look at your equation sheet and you can see momentum is equal to mass times by velocity. So in this situation, substitute in your values, 0.216 equals 180 grams times by velocity. Now what should be jumping out at you is that momentum is in kilograms meters per second, but your mass is in grams. So I would convert that at this stage. So 0.216 equals 0.180 kilograms. So divide it by 1,000 to put it into kilograms, times by our velocity. So rearranging it, 0.216 over 0.180 equals our velocity. And if you put that into your calculator, it gives you an answer of 1.2 meters per second. Question 3.2. The train collides with a stationary carriage on the track. Explain why the velocity of the train after the collision is less than it was before the collision. Use ideas about momentum in your answer. So the key thing is that you're talking about momentum. You're not talking about energy loss or forces in this situation. You're using the idea of momentum. Okay? Now, what is the law of momentum that you've learnt? Is that momentum in a system is conserved in the collision, which means the momentum before is the same as the momentum after. But during the collision, the momentum of the carriage, which was stationary, increases. Okay, so the carriage itself is then moving, where it was stationary before, because the train has collided into it. So because of that, you think the momentum is now being, and that is the same as the before and after. So momentum in that as input equals the output, but now it's pushing a bigger mass. It's pushing the carriage as well. This means the momentum of the train decreases. Okay, so therefore, because the mass of the carriage and train is greater, you've got the same amount of momentum, but now the carriage and the train are going together, and therefore the velocity would decrease. Okay, since velocity would be equal to momentum over mass. Okay, and those would be your 4 marks there. So it's recognising the fact it's all about the idea of conservation of momentum. Okay, question 4 then. A teacher demonstrated the motor effect, which figure 5 shows the equipment used. So you've got your 2 magnets and a current carrying wire. Explain why there is a force on the wire when current is in the wire. Okay, so this is about obviously the motor effect and forces being exerted on a wire, which would either go up or down. But why does that force actually occur? Well, what you would need to recognise is that there is a magnetic field going between those two current bar magnets. Now, if I then got a current going through a piece of wire, then you get a magnetic field around that wire. When you've got two magnetic fields that are clashing, that would exert a force, okay? And that is your answer. So I would say there is a magnetic field between the magnets. Remember, it goes north to south. A current carrying wire also produces a magnetic field, be circular around the wire. When field lines clash, a force is exerted. Okay, question 4.2. Explain how the direction of the force on the wire can be predicted. So I'm looking at how can I know which way the wire is going to go. Is it going to go up or is it going to move down? Well, how would you work it out if they asked you to in an exam paper? You would use Fleming's left-hand rule, which would be your first point. You would use Fleming's left-hand rule. And this question is basically getting you to explain how you use Fleming's left-hand rule. So you point your first finger, point first finger in the direction of the field of the magnet going from north to south. You point your second finger in the direction of the current. Okay, and then naturally your thumb points in the direction of the force. So you get 1 mark for saying Fleming's left-hand rule, 1 mark for describing where your fingers go, 1 mark for describing what the thumb does. Okay, you could, if it was a 4th mark, add in the fact that you would hold your thumb, first finger and second finger at right angles, but this is the key point. Question 4.3 then, figure 6 shows a simple electric motor. Explain one way that the motor could be changed to increase the rate at which the coil rotates. So what could I do to make my coil spin faster? Now you've just got to explain one way. So although you've got multiple ways, you've just got to explain one. So looking at the motor, what could we change? Well, we could change the coil. We could increase the number of coils on it. Okay. What could I change about my magnet? I could use a bigger, stronger magnet. What could I change about my cell? I could then increase the potential difference or current in the cell. Okay. Yeah, and those are your 3 variables that you can use. But why, doesn't matter which one you use or decide to answer with, why does that actually make it go faster? Because if you've got more coils, a stronger magnet or more potential difference, what's that going to do? It's going to exert a bigger force on the coil and therefore make it spin faster. So I would just answer, use a stronger magnet. I could say any of the 3 things listed there, which would exert a stronger force on the coil, making it spin faster. Okay, so question number 5 then. A student investigated how the colour of a surface affects the amount of infrared radiation the surface absorbs. Figure 7 shows the equipment used. There are 2 flasks painted in different colours. You've got an infrared lamp, a timer, and you've got a black flask and a white flask, but they're different. This is the method used. You pour water at 20 degrees Celsius into each flask. You place a bung and a thermometer into each flask. You place each flask in front of the infrared lamp and you measure the temperature of the water every 30 seconds for 10 minutes. Explain 2 improvements to the method the student should use. So first of all, I'd be thinking, right, what is wrong with this method? What have they not controlled? Well, the first thing that jumps out at me is that the flasks are different, okay? They're in a different shape. The second thing is they're not exactly the same distance, or there's no way of measuring and ensuring they are the same distance. That's wrong. And then you could also say it's just said pour water. It hasn't said how much water, it just says pour some. So those are my key improvements that jump out at me. But you've got to explain them. Okay, why does that have an impact? What should you then do to make it better? So if I take the shape of the flask to begin with, so they should use the same shape flask as different shapes have different surface areas to absorb and emit heat. That would be my first improvement. That would be 2 marks there. State the improvement and explain why. The second thing that I would do is make sure they're the same distance. How would I do that? Well, I'd use a ruler. Okay, so make sure that is measured accurately with a ruler. And then why is that important? Well, if it's further away, there's going to be less infrared radiation potentially hitting it than the other one. So ensure flasks are at the same distance from the heater or from the lamp. Okay, using a ruler. This ensures they are exposed to the same amount of infrared radiation. Okay, and that would be another 2 marks. Figure 8 shows the results for each flask. You've got time in seconds and temperature in degrees Celsius. So you've got your white flask and your black flask. Complete the sentences. After 100 seconds, the temperature difference between the black flask and the white flask was what? So you want to work out the temperature difference at 100 seconds. If I go to 100 seconds, I can see my white flask is at 24 degrees Celsius. If I go to my black flask and read across, it's halfway between the line. Draw the lines on in your exam paper with a ruler, and you should see it's roughly 31.5, or exactly 31.5, sorry. So what you would then do, calculate the difference, take it away, and that would give you 7.5. They would also accept 8 in this answer, in case you got 32 when you drew your line. The temperature of the white flask stopped increasing. The temperature inside the black flask continued to increase for a further blank seconds. So, you know, at 200 seconds, the white flask has stopped going up. How much longer did the black flask keep going up for? Well, look where it stopped, okay, and went flat, and then you've got to read your graph. Okay, go down, and you can see that the black flask stopped heating up at about 440 seconds, if you read it down. So how much longer is that? From 200 seconds, it's 240. 440, take away 200, is 240 seconds. Question 5.3. The initial rate of absorption by the infrared radiation by the black flask was greater than the initial rate of absorption by the white flask. How does figure 8 show this? Well, if you look at your graph here, you can see your black flask is going up more quickly than the white flask. But how can I describe it? Well, the steepness of a line is the gradient of the line. So that's how the graph is showing it. Quite simply, the black flask has a steeper gradient. Then, question 5.4. Explain why the temperature of the water in the flasks increases and then becomes constant using, and this question is about infrared radiation, so you should be linking in infrared radiation the whole way through. Okay, so what then happens is, first of all, why is it increasing? Well, it's because the flasks, and I would make this point clear at the beginning, the flasks absorb both heat radiation or infrared radiation. They absorb both infrared heat radiation and emit infrared radiation. So they absorb it and they emit it. The temperature increases at the beginning because more infrared is absorbed than emitted. Okay, causing the temperature to go up. Now, when it starts heating up or getting hotter, the rate of infrared radiation being emitted from the flask would also increase. So, as the temperature increases, the rate of infrared emitted would also increase until there is a balance where infrared absorbed equaled infrared emitted. So you're absorbing the same amount as you're emitting, and then this causes the temperature to become, using the word that they said in the question, constant. Okay, so slightly difficult question there. Again, not many people got 4 marks on it. A lot of people dropped this 3rd mark here, but actually the 1st mark. Okay, so you got the idea that the temperature increases because you're absorbing more infrared radiation, but then it's about the balance and then it becoming constant when it is balanced. Okay, so that is the end of question. Okay, question number 6 then. The thinking distance, or the distance a car travels during a driver's reaction time, is called the thinking distance. Figure 9 shows how the thinking distance depends on the speed of the car. So you've got the graph here, you can see speed of the car is increasing and the thinking distance is increasing. So determine the driver's reaction time. So if you know from the equation sheet that distance equals speed times by time, rearranging it would then give time is distance divided by speed. So we can just use any 2 values on our graph that correspond together. So I personally would just go with the end of the line, and I can see my distance that I've travelled is 21, my speed is 30. So therefore just substitute that into your calculator and that gives a reaction time of 0.7 seconds. Okay, and that is your final answer. Question 6.2, figure 10 shows a velocity, or how the velocity of a car changes during braking, and it gives you a velocity time graph. It then says determine the braking distance of the car. So what you should remember is on a velocity time graph, the area underneath the line is equal to the distance. Okay, so the total area is equal to the distance. Now, in most past paper questions, it is a straight line. They've made it quite difficult now because it's a curve. So what you'd have to do is work out how much one square is then actually worth. Well, if I've got a distance of 5 in 1 second, that gives me a total distance travelled of 5 metres. So each square, I know that each square is equal to 5 metres. The next part is where a lot of people went a little bit wrong. You then need to know how many squares you've actually got. Okay, now this one is quite hard because you've got to try and match up how many small parts of a square would then fit together. Okay, so I've got 4 there by using, because this square is missing a little bit, but you've got another little bit here. And then if you do it in total and you add up all the different squares, supposedly you get to an answer of 9 squares. So there's 9 squares in total. But what it does allow you is that if you miscount, or it is quite hard to do, matching them up, you're allowed any value between 8.5 and 10 squares. So if you went with 9.5 squares, you'd still get the mark, and it would be allowed error carried forward. So that would get you 2 marks. 1 mark for working out that each square is worth 5 metres, 1 mark for getting the total number of squares between 8.5 and 10. So to calculate the total breaking distance, you would just do 5 times by how many squares you put. So if I put 9 squares, 5 times 9 gives me a total breaking distance of 45. If I said there was 10 squares, 5 times 10 is 50 metres. Whatever value you got for your number of squares, they would accept as long as it was between 8.5 and 10. Okay, question 6.3 then. Explain how the gradient of the line on figure 10 shows that the resultant force of the car was not constant. Okay, so we're linking the gradient of the line to the resultant force on the car. Now, if I go back to the graph, we can then see that our line is a curved line. But what is our curved line actually showing us? Well, if I've got velocity and I've got time taken, my equation that links them, acceleration is change in velocity divided by time taken. So my gradient of the line is actually equal to the acceleration. So that would be my first thing I would say. The gradient of the line is equal to the acceleration. So you've clearly determined that. And we can then see that the gradient of the line is not constant. It's not a straight line going down. You could just say it's a curve. Okay, so what you might have missed off the first point, everyone should have been able to get this mark here just by saying the line is not constant. So therefore, because the gradient is not constant, the force is not constant, because force is directly proportional to acceleration. Okay, so remember, F equals m times a. So if your acceleration is going up, then your force must be going up the same amount. Now we can see here that we've got a curve going down. So therefore, our force and our acceleration are not directly proportional. So 1 mark for stating that the line is linked to acceleration, or is the acceleration. We can see that it's not a constant straight line, it's a curve. So therefore, the force is not directly proportional to the acceleration, would be our 3rd mark. Question 7 then. Figure 11 shows a stationary apple hanging from a tree. The X marks the centre of mass of the apple. Draw 2 arrows on figure 11 to show the forces acting on the apple. So we can see here there's 2 marks towards the end of the paper, and it's a relatively easy question. So everyone should be able to get marks on this part of the paper. So therefore, I know I've got two forces acting on it. All forces act from the centre of mass, and they act in opposite directions. Now, in order to get the marks here, you need one mark. Well, one mark is just the vertical arrows going in opposite directions. But because it's hanging from a tree, the apple would be stationary, and therefore the arrows should be the same sizes. So it's one mark for two opposite arrows, and then one mark for them being the same size. Okay, because remember, if you've got balanced forces, the object is either stationary or moving at a constant velocity. In this case, stationary. Question 7.2 then. It takes 0.5 seconds for the apple to fall to the ground. The initial velocity of the apple is 0. The acceleration due to gravity is 9.8. Calculate the distance fallen by the apple. Use the physics equation sheet. Now, it's a 6 marker, so that's kind of telling you, it probably is two equations you need to link together, and it's given you the initial velocity. Now, there's only one equation that gives initial velocity, which is the final velocity minus the initial velocity equals 2 times acceleration times s, which is your distance. So we want to be calculating our distance, which is s. However, we haven't got all the information we can put in here, because whilst we've got initial velocity, that should be squared as well, so 0 squared, if I put in what I don't know my final velocity. 2, I don't know my acceleration. I do know my acceleration, 9.8, and obviously I don't know my distance. So I can't use this equation yet until I've got the final velocity of my apple. So in order to find my final velocity, I also need to look what I've been given. So I've got time. So I look at my equation sheet and I can think, acceleration is the change in velocity divided by the time taken. Okay, so I know my acceleration is 9.8. So my change and my time taken is 0.5. So rearranging this equation to find my change in velocity, 9.8 times by 5 gives me an answer of 4.9 meters per second. So this is then my final acceleration. It started at 0, it's ended at 4.9. So what I can then do is substitute that into my equation here. So 4.9 squared minus 0 squared equals 2 times 9.8 times by my distance. Then, if I want to rearrange it, obviously 0 squared is nothing. 4.9 squared over 2 times 9.8. Put that into your calculator correctly. You can break it down by doing the squared part first, but that should give you a final answer of 1.2 meters. And that is your final answer for 6 marks. Okay, last question then. This is question 7.3. In question 7.2, it was assumed that the acceleration was a constant 9.8 meters per second squared. Evaluate this assumption. So evaluate, you're either agreeing with it or against, and you need to explain why. So if I break it down and I'll do both arguments, I'll say yes or why this is not true. Okay, so not true, and then I'll say it was true. So is 9.8, is it right to assume that 9.8 meters per second squared, the force due to gravity on an object, is constant? Well, if I think about my apple and it's falling down to Earth, as the apple is falling down, what is going to happen to its speed as it falls down? Well, as the acceleration is 9.8, the speed of my apple will get faster. So the velocity or speed increases. As my apple is falling down, what's it going to be hitting? Well, it's going to be colliding with air particles. So what's going to happen to my apple as it goes and it hits more air particles? Well, as it hits more and more, the acceleration would then actually decrease because there'd be more drag or reaction force on the apple. So I would then break it down like this. So as the apple falls, it accelerates. Okay, you've been told that, you know it's accelerating downwards. But it hits more air particles. Therefore, the force, or the resultant force, decreases. So therefore, the acceleration would then decrease. If I'm hitting more air particles, my resultant force would then be smaller, and therefore the acceleration would go down. So therefore, it is therefore wrong to assume it is constant, or 9.8 meters per second squared constant. Okay, so that's an argument of saying how forces might therefore affect the acceleration and it not being constant. Now, you could also argue that 9.8 can be a constant force. Well, why would that be? Well, the apple only falls a short distance. Therefore, air resistance is negligible or very small. So the resultant force would be constant, and therefore we can assume that using 9.8 is constant. Okay, because it would be falling at a constant speed, because the effect of air resistance is negligible. So it almost kind of goes back to that terminal velocity answer in terms of the effect of air resistance on the speed of objects. Okay, so that's the end of this paper then. Was a tricky last question, but hopefully you found it useful. Thank you very much.